Hi, all. Welcome to Theoretically Podcasting. I'm Vasu Sham, and in today's solo episode, I thought that I would talk about something that I am even more unqualified to talk about than my usual episodes, which is the interesting topic of so-called neural scaling laws. So, we've all seen and played with, probably by now, GPT-4, ChatGPT, maybe GPT-3, um, and perhaps also played with some of the image generation models like DALL-E. And perhaps we're wondering how big of an impact these will have on our technological future. So, what these models will start to do beyond amusing lots of people on the internet. Clearly, they're capable of a lot more. And there are a lot of companies near where I live which are indeed hoping that these technologies will play a key and pivotal role in shaping our technological future. So, for better or worse, they're here to stay, and we'll hear a lot about them. And we're also going to hear about them on this YouTube channel, apparently. But the specific angle I will take has to do with certain gross performance metrics of these models. And what we'll see is an observed scaling relationship between the loss or objective function of these neural networks on unseen examples as a function of the number of parameters or the number of data points or the number of flops, floating point operations per second. And these will be log-log plots, and we'll see a linear relationship. So that basically, there seems to be some scaling law that the loss on unseen examples of these neural networks seems to obey. And the relevance of these scaling laws is what I want to try and explain here, which is that they provide a guide for what all of these companies should be aiming to do in order to build ever better models. Now, the other reason I wanted to cover this is basically to try and point towards where these scaling laws seem to come from, which is something I find very interesting. And hopefully, I'll convince you all that they seem to be an aspect of our world. So they seem to be an aspect of the data that's being picked up on and sort of stretched out in these models in the form of their loss. So that's going to be the goal of today's podcast. It's certainly a slight departure from the normal format, and so I appreciate your patience, and please wish me luck. So let's begin with looking at some of the relevant graphs. So here's a little document that I've prepared based on some very nice references, which I will link in the video description. But basically, the empirical observations are all of the following type. The idea is we plot loss as a function of the number of parameters or the number of data points, which are denoted n and t in this particular reference, and the number of data points or number of parameters on the x-axis. Now, there is another plot like this that one can make for the number of units of compute time as well. And in all those cases, the loss seems to obey the following trend. So what we're talking about here is the loss on unseen examples, which is a performance metric typically used to measure how well a trained neural network is doing at whatever it is it's trained to do. So very briefly, for the physicists in the audience, what we're doing when we train neural networks is we're setting up a gradient flow, discretized in the appropriate way, on a space of network parameters. And the function whose gradient we're taking is the loss function, that is basically a comparison between a given target and the network function, the actual neural network, being applied to the data. So if all those words don't mean very much, doesn't really matter. The basic idea is that the neural networks are trained to minimize this loss function, but they're trained with some amount of data that's been sort of set aside for that purpose. And what we actually want to do is apply these neural network functions on unseen data. Now, when it comes to the very largest models like the generative pre-trained transformers, the GPT models of OpenAI, or PaLM or any of the other big models, this is a bit peculiar because they're trained on such large parts of the internet that, picking up a characteristic example, which is a sample of text, like what's been written somewhere on the internet, is it's a little hard. But let's just say that it's almost certainly true that in all of these cases, the models do very well to predict the next token in the case of the generative pre-trained transformers, or say if we're just talking about some much more modest neural networks like classifiers, to classify data that they have not seen in their training data. So that's why this loss on unseen examples is a performance metric. So it would be nice for it to be low. Let's just put it that way. And the trend that's observed, mostly talk about this dotted line, this black dotted line, is a power law. Right? So we're on a log-log plot. We see straight line. We should expect that this is a power law. Okay, so this is just a cartoon illustration in one of these papers. What the actual plots look like from some of the other references is of the following type. So here we're looking at training loss as a function of floating point operations per second. And here we're looking at the number of parameters. And so this is not quite the same as the test loss, but it's the training loss. Nevertheless, here we have the test loss from one of the original references as a function of compute, dataset size, and parameters on a log-log plot. And we're really seeing how these trends work out. And so what's the formulaic takeaway? The phenomenological model to explain this behavior is given as follows, and this should be reminiscent of old-fashioned Landau theory, and at least that's what it reminded me of. You see that there's a scaling formula for this test loss as a function of the number of parameters and the number of data points. All of these alphas and NC and DC are fit constants. And we'll see basically what they're doing. So very quickly, say we took the number of data points to infinity, the loss decays as a function of the number of parameters. So that's very nice. This is decaying behavior with the one parameter we have control over. But now let's say that it isn't strictly infinite, but it's significantly larger than n, that the number of data points is just significantly larger than the number of parameters. Then what we see is that the test loss is basically behaving in the same way, except that it's sort of bottlenecked by this number nc, which dictates when this loss function will plateau. So there's basically some number of parameters at which we're not seeing decaying behavior anymore, right? So basically we're looking at when nc over n reaches sort of order 1. That's when we don't have constant improvement by just increasing the number of parameters. Conversely, take the number of parameters to infinity, and the test loss decays as a function of the number of data points. And again, if this isn't truly infinite, then there's a plateauing behavior set by this constant d sub c. So now there were a couple of references which I will open, one by people at OpenAI, the other from DeepMind. There have been a lot more papers about this phenomenon. These are just two of the very notable ones, where there was a slight difference between the observed exponents. And we'll go into the reason why they seem to observe this difference. And the follow-up paper, which is what people take to be the state of the art, as far as I can tell, please forgive me if I'm getting any of this wrong, predicts that these two exponents are roughly equal. And what that means is that the effect of the number of parameters and the effect of the number of data points is commensurate. So what's the right thing to do? Well, the right thing to do is to take a double scaling limit. So we scale the number of parameters with the number of data points in a particular fashion so that we don't see any plateauing behavior, right? So we just continue to see certain falling trend. So let's put in the minuses. No, these are all in the numerator. Okay, never mind. So basically we continue to see a decaying trend with the increase in the number of parameters and data points scaled appropriately. So already at this point, what can we say? What we can say is that in order to make these models better, it's important that they become bigger and that we have more data. So this might sound very obvious, but we should note that the alternatives include aspects such as architectural improvements or better optimization methods. And although all these things do matter in controlling what the various values of these exponents are, what's driving the decaying behavior of the loss itself seems to be size. So this is basically the reason that we have all of these fine startups in the vicinity of where I am now, investing so much money into buying compute and in basically getting their hands on as much data as they can. Because this seems to be the way to make these models reliably better. Now, I will try and contrast this gross performance metric with some less smoothly varying ones, which have to do more with specific model capabilities. And we'll see that there, we're not actually seeing a smooth increase in said capabilities, but we do actually see sharp jumps. And we'll get to that a little bit later. But now let's sort of try and understand what's going on here, setting aside as many details as we can. And in fact, it seems, and there have been papers written by some of the authors in the references previously, that the scaling behavior isn't limited to just, transformer models or some of these larger, more intricate architectures, that even relatively simple regression models, kernel-rich regression models, linear models, trained on fairly simple loss functions, so not just the cross-entropy loss, which was the subject of some of the original references, have a similar behavior. They also seem to exhibit some of this scaling behavior. So here we see some plots for the loss, basically in a student-teacher model, so-called student-teacher model, which is a much simpler sort of modeling technique than the sort of large neural network. And we still see a very similar kind of behavior. And this is just for mean squared error, so a very simple quadratic loss function. And now you can also sort of go to more classic data sets and just train them with more modest neural network architecture, so-called convolutional neural networks. And so here we see that there's a similar kind of behavior as well. So the scaling behavior per se seems to not be limited to just the architectures used in the most recent large models. And what's the upside of that? The upside of that is that we can probably get some idea for why such behavior should occur by analyzing just these simple models. And we'll get to that. Now, what also seems to be happening is that the scaling behavior really is some aspect of the data itself. And this is something I've alluded to. And what that concretely seems to mean is that if we look basically at the covariance matrix of our data, which is typically represented in some large these large vectors, and we simply sort of average over the example index alpha and keep the feature indices. So we look at this covariance matrix. These matrices these eigenvalues of these matrices seem to satisfy a power law decay with respect to their magnitude index. So if you just sort the eigenvalues as we normally do, then starting at a certain eigenvalue, there seems to be this kind of power law drop off. And so this has actually been worked out for some known data sets, one for image data set here that's been shown, and another one for text data set. And so there's some region here where there seems to be the scaling behavior. And then basically by subsampling the number of features, it seems like this this behavior can be stretched out. And furthermore, in a toy model that will be used in one of the references I'll try and go through, seems like performing some nonlinear transformations like applying random features and so on seems to extend the power law behavior of these eigenvalues a little bit further. So if you basically take not just a matrix, but the matrix of certain nonlinear transformations applied to the data, then go and diagonalize it, seems like we're getting stretched out power law behavior. So the interesting takeaway from this is that the reason we can have large language models growing ever better with just increase in their scale is some aspect of the corpus of natural language they have access to in their training data itself. And that this doesn't seem to be limited to text. This behavior seems to also manifest for images and all sorts of other things. So this I thought was a very interesting thing to note, that there's a hidden power law behavior in the sort of spectral properties of data itself. So now let me open up some of the original references from which I was taking some of the plots, starting with this one by people at OpenAI. And in this paper, this is sort of where I got the plots that I was showing in the little document I had earlier. So here's where they laid out the basic observation of the scaling law behavior of large models trained with so-called cross-entropy loss. So what they observed was sort of summarized here. And so for models with a limited number of parameters trained on sort of large data sets, they observed the following scaling behavior with alpha n 0.06 and n sub c being 8.8 times 10 to the power of 13. Note that that's a number of parameters. So these were not experiments that they ran on a little laptop, just, something to note. And then for large models trained with a limited data set and with early stopping, what they saw was, again, a scaling behavior with alpha d 0.095 and DC of this many tokens. So again, tremendous amount of data. One more quantity that they were looking at was basically limiting themselves by an amount of compute with very large data set and sort of optimally sized model, optimal based on this calculus up here. And they find the following very similar behavior. And just note that this is 10 to the power 8 petaflop days. Okay, so please Google that to know what sort of scales we're looking at here. So wonderful work, and see, this is how they ran into this phenomenological formula for L. And note that here they saw that alpha n and alpha d were different, and that, basically because these are decay exponents, just seemed like it was better to make these models larger. That was sort of like the biggest effect, the most important effect. And then there was an interesting follow-up a sort of year later by all these people at DeepMind. And what they managed to do was rerun this kind of analysis. And basically, what they were a little bit more careful about was setting some hyperparameter tuning. So they were basically scheduling learning rates a little bit more cleverly. And what they found was that data mattered just as much as the number of parameters. So in their model, so I'll see if they write down a formula like this. So here's the rough formula, and then basically for them the exponents are sort of very similar. And what they basically do is also train model chinchilla, named as such because it's much smaller than the other models that they were comparing it to. And what they managed to show was that by training this 70 billion parameter model with 1.4 trillion tokens and comparing it with a larger model trained with less data. So let's sort of go and check if they've described what the actual numbers are. I think it's somewhere in the sort of early parts of the paper. So basically what they find is that yes, they're larger models like Gopher with sort of 280 billion parameters, 300 billion tokens, versus a smaller model like Chinchilla with 70 billion tokens, 70 billion parameters and 1.4 trillion tokens. This seemed to outcompete this model at more or less everything. So this was a sort of proof of concept that their analysis was correct, that the data mattered as much as the number of parameters, basically that there was a way to take both of them to be large in an appropriate manner, and that would lead to the biggest effect. So here's a nice little blog post from Less Wrong, where the difference is sort of explained a little bit better. And so this was I'll just refer my viewers to this because I'm probably going to do a much worse job at explaining it than this nice paper does. So with that in mind, what would be interesting now to do would be to look at some of the analyses people have tried with simple models to try and explain the scaling behavior. And so first, with again, Jared Kaplan, who was the lead author on the original OpenAI paper, along with Sam Candlish, here's a paper where they were trying to explain this phenomenon of neural scaling by understanding the so-called data dimension, or the intrinsic dimension of the data manifold. And so very briefly, what they were trying to posit here was that, so here in the main ideas section, they kind of go into it. The idea is that neural models map the data to a manifold with intrinsic dimension D, And then they use added capacity to carve up this model into ever smaller subregions. So added capacity is basically whatever the neural network is doing. If the underlying data varies continuously on the manifold, then the size of these subregions, rather than the number of the regions, determines the model's loss. To shrink the size of the subregions by a factor of 2 requires increasing the number of parameters by a factor of 2 to the power d, where d is the intrinsic dimension. So the inverse of the scaling exponent 1 over alpha will be proportional to the intrinsic dimension d of the data manifold. So remember, alpha is basically the scaling exponent appearing here when we have, say, an infinite amount of data and we have a fixed number of parameters. So this was sort of the intuition behind the analysis they perform here, and basically they find some amount of resonance. Now, there have been other analyses performed too. So again, like, the reason why I wanted to point this out was that this again alludes to the relationship between some aspect of the actual data and the observed scaling behavior of the loss. So this explains certain regime of the general formula I showed before, where we have d large and n fixed. And there was another paper. Well, I mean, there were several other papers, but here's another paper by some of the same authors where they were explaining neural scaling laws in the context of kernel learning and with some linear models. And basically, they were this is where I got some of the plots for the smaller models, such as the convolutional neural networks, and also for the student-teacher models. So basically, that's somewhere deep in the analysis that basically you had these image models and then these student-teacher models, which also seem to be exhibit very similar behavior. And they have a nice explanation for this phenomenon using their kernel methods. But what I wanted to get to was this gargantuan paper written by Alex Maloney, Dan Roberts, and James Sully. So this podcast will always highlight people from HipTH, inevitably. So that's the implicit bias of this podcast, but okay. So here they have a solvable model of neural scaling laws, which is based on, what they do is an analysis based on random matrix theory to basically take both the number of data points and the number of parameters to infinity in a sort of scaled way. And so it's going to be really hard to get through the entire paper. I'm not even going to try to do that, but it touches upon several of the things we've already discussed. So this first section, the second section, I really recommend for everyone to read, just because it gives a nice overview of everything that we've been talking about. Now, what they do is they set it up. They set up this problem using a sort of student-teacher model involving features. So these features are some transformation of the data, and then what they do is they basically choose so-called so they basically choose to embed the data into a larger feature space and apply some nonlinearity to it. That's their phi sub j, and then they're basically comparing such a model. Okay, so basically they also pick certain kind of data, right? So that's kind of what the model, the analog of the network function does, right? And then they pick some kind of data. So this data they're picking is basically they're picking the distribution out of which they're drawing the data, and what they choose is for the data to have basically some covariance where the eigenvalues of that covariance have the following density. So you see there's this power law baked into the eigenvalues of the covariance itself. And then they basically set up the random feature model, which is basically given with these features. So here there's no nonlinearity, basically. And they just do linear regression on this loss function. So targets minus the z's. And then they add some regularization. So if these words don't mean much, all you need to know is that they have a model which is quadratic in parameters, the tunable parameters, and in the features. So what they do is find a way to average over the appropriate quantities and try and actually look at the trained model's loss, which is a possible thing to access here because actually solving for these thetas is fairly simple, right? So they're actually able to solve for what the parameters have to be in order to minimize this loss, plug that back into the loss. So it's very much like going on shell from, from the perspective of action principles, like going on shell of the action and asking, well, what's the lowest on shell action? And they use basically sort of techniques from random matrix theory to compute the averaged loss on unseen examples. And so they managed to do this in basically a way that they can ask both about large number of data points and a large number of parameters. And after no shortage of detailed analysis, some nice diagrammatics that they developed. But again, this is just scrolling slowly so that you see that this was also quite a bit of effort. They're basically able to find this kind of result, and they're basically able to show that in the regimes that we're interested in, we recover the right behavior. So this is basically sort of model of what's happening even with the GPT and other such things. But what it's doing really is it's basically taking okay, so let's go a little bit faster all the way down to their analysis of linear models. But okay, so let's just run through their analysis of linear models and see where the scaling behavior truly comes from. Okay, so here there's no feature space, so the weights apply directly to the inputs, and the data comes from some distribution with some covariance. And the covariance seems to be the only thing that's relevant here. And the reason for that is that we have a loss which is basically quadratic in everything involved, and we also know how to solve for the parameters given that we want the loss to vanish. And you see that what they do is they basically find that the solution has within it the feature resolvent. So this is a resolvent, much like what we're used to seeing in random matrix theory, with gamma, the so-called ridge parameter that sets the regularization, playing the role of the spectral parameter with a minus sign. So there's some differences there, but basically they can define the test loss. So they basically know how to apply this function, right, given some training data on data that's unseen, right? So that's the object we're actually after. And the idea is to be able to average over this thing, given some, we're basically averaging over random noise and label weights and so on. So what they eventually find is a result that looks like this. So they're able to write this as some differential operator in terms of the ridge parameter. And note that if we're taking derivatives of the resolvent and related objects with respect to the spectral parameter, we're really asking about density correlation functions. So they're basically relating the average loss to some kind of density correlation function. And then their interest is in taking gamma to 0. And when they do that, they basically are able to write the average of L, basically the test, what they call the test loss, as a function of delta -1 and delta 0, where delta is this thing. So this result, this kind of quantity, satisfying some self-consistent equation. And then what they show is that, well, you see, if you choose just sort of isotropic features, just random features, the so-called Marchenkov-Pasteur distribution, what you're eventually going to get isn't quite of the kind that that we're expecting, right? So the result they had with arbitrary data distribution is not by itself pointing to scaling loss. That's the only point I'm trying to make. But if you choose power law data, where basically the covariance has a spectrum which itself has some power law behavior, then we actually see that there's some reproduction of the scaling behavior, the sort of power law behavior of the loss on unseen examples. So it seems like whatever's happening is that the power law behavior within the data is sort of being processed by the model, and it's sort of being observed at the level of the loss. So it's sort of in concert with what people in the other papers were pointing or alluding to as well. So and so this is a very nice reference. I recommend everybody viewing to go and check it out. But what we see here is that the scaling behavior, right? If we thought about it from the perspective of like the Landau theory, is a consequence. This gross behavior is a consequence of some aspect of the data itself. But note that this gross behavior in and of itself, or the fact that we're seeing it in all these simple models, isn't necessarily so that doesn't tell us that if we're interested in building powerful, capable models, that this is any useful information, because clearly having a low loss in and of itself doesn't tell us very much, because having a low loss in a kernel model means the model does what you expect it to, right? Which isn't much. Whereas with all of the architectural sort of discoveries and innovations that have occurred in the past decade, what we know is that these large models, right, these transformer models and so on, have the ability to pick up powerful capabilities at certain thresholds. So there's a nice paper by Anthropic, which is the company that Jared Kaplan is now with, which is basically focused on AI safety. And they have a nice paper about capabilities that can be picked up, but that might not be necessarily a good thing. So basically, when you have emergent capabilities, the downside is that they're also sort of emergent harms that the large models are capable of. So it's very important to understand what these are. So here's the paper I was talking about, which was predictability and surprise in large generative models. And so many authors, all from Anthropic. And here what they point to is basically that there are these smooth general capabilities that satisfy the scaling laws that we've been discussing. But what's relevant almost is the fact that there's abrupt specific capability scaling. So the point of modern artificial intelligence systems is that they're capable of a lot more than what on paper they're trained to do, right? So that's what sort of separates the more cleverly designed and more powerful models from these sort of simple kernel-like models just scaled up to very large size. And you see there are these capabilities like 3-digit addition that only start if you have a model with a number of parameters significantly larger than, say, 10 power 9. I mean, you actually have to go up to 10 power 10 and beyond, and that's when it starts to become good, right? And if you want it to be really good, you want to be somewhere at 10 power 11. And now if you want to have like program synthesis, so if some of you are using GitHub Copilot or anything, there you see that it's really again at this 10 power 11 mark that you see a sharp increase, and similarly with language understanding. And so this is a very nice paper. I really recommend people look at it, because it really also goes into some of the more societal implications of what these abrupt capabilities or these abrupt capability acquisitions could imply. Now I see that there's things like recidivism prediction, black to white false positive ratios, and so on, which they also look at. And so Also, it seems like there's this increase in toxicity with the the number of parameters. So it's not necessarily always a good thing, but on the other hand, here, if we were to go back to our analogy in terms of the Landau theory of phase transitions, we see that this transitional behavior is sort of requires something like Landau-Ginsburg. We're not just looking at like the gross loss, but we're looking at some more fine-grained details. And it would be very interesting to see what one can do on the theoretical front to be able to predict some of this. So basically, if there's a minimal model where one can actually see that there's a sort of abrupt capability acquisition, and what this phenomenon rhymes with another phenomenon called grokking, where basically the loss on seen examples and unseen examples has a large gap up until the training reaches a certain point, and all of a sudden, after like an exponentially large number of uh, training time units, the loss on unseen examples also sort of plummets. And so all of a sudden, it's like the model has learned whatever it is. So it's sort of grokked whatever it is that we're training it on. And a sort of minimal model of grokking might be able to give us some handle on understanding these phenomena as well in the very large models. So anyway, I hope you've enjoyed this presentation, haphazard as it was. And I do want to come back and discuss some of these topics, ideally with maybe one or more of the authors of the papers I was discussing, or with some of my more machine learning inclined friends or friends of the podcast. But for now, if you've made it this far, please consider liking, sharing, and subscribing. This is Theoretically Podcasting, and I'll catch you next time.